um, David, can you see the screen?
Yes, yes, Prof. I can see the screen.
Okay, okay. Thank you. Okay, the first problem says there is a 8 by 8 chessboard. Of course, it means it's got 64 squares in it. In how many ways can you place one black rook? Now, this kind of assumes that you have a knowledge of the names of the pieces, but it's not a serious matter. Uh, you can call this rook any piece you like. You want to place one black rook and one white rook on two different squares that are on two different rows in the same column. And two different columns. Okay, let me just try to get my act in order here. All right, I'm on my way now. So you got an 8 by 8 um, chessboard. Okay, I don't know whether I'll be able to draw the entire 8 by 8, but we'll just have to imagine. Okay, and then you got these columns going down like that. Okay, I'm not filling up everything. So you got a section of this chessboard. Yeah. And the question is, you want to place one black rook I want to place a black rook here. Let's just place it somewhere. Uh, and then you also want to place a white rook, but they must be on two different rows and two different columns. In other words, the white rook cannot be on this column and it can't be on that column. So, or at least on this row, which I am pointing to, I don't know whether you can see it. It's not allowed to be on this row, and it's not allowed to be on this column. So the question is, how many ways can you do this? Okay, so let's just uh, give a different color to the other rook. So like for instance, the other rook can be here. All right. So in how many ways can you do this? Now, there are only two choices you have to make. You have to make the first choice and the second choice. So we'll put that in a block like this. So the first choice can be made in how many ways? Well, you got the first rook can be put anywhere on this entire chessboard, and there are 64 squares. So you got 64 choices. You got 64 choices for the black rook. And for the white rook, now you're not allowed to put the white rook anywhere on this column or on this row. So how many squares are you not allowed to put it in? So if you count white cannot be placed the white cannot be placed in any one of how many squares? Okay, you got 8 here and you got another 8 here. So that's 8 plus 8. But then you have to, this square will be counted twice. So you have to remove that second count to count it once. Or if you like, you can say it's 8 plus 7, because you must avoid this square is already counted. So, so that is equal to 15 squares. You cannot place it in 15 squares. So in other words, in how many places where you can place it, so it can be placed in 64 minus 15, which is 49 squares. So the number of choices for white is 49. So we've seen this kind of thing before. The first one can be chosen in 64 ways, and the second one can be chosen in 49 ways. So therefore, number of ways is equal to 64 times 49. Which is actually 56 squared. 8 times 7. And 56 squared is 3136. You can multiply it out. You're not allowed to use calculators. And you can get the answer to that. I have a quick way of calculating a square number. I can tell you. If I want to calculate 56 squared, I go to the nearest multiple of 10 to 56. And I ask myself, how far is it from the nearest multiple of 10? 56, and the nearest multiple of 10 is 60. How far is it? It's 4 removed. So what I do is I subtract 4 squared and add 4 squared. Same thing, I'm just subtracting and adding the same number. But why do I do this? Because this part here is a difference of 2 squares. 56 minus 4, that's 52, and 56 plus 4. 4 squared is 16. Now this is easy to work out because now you got 60 times 52, and that's just 6 times 52, which is 312. 6 times 52, and there's 0 there, plus 16, and 3120 plus 16 is 3136. That's what you got there. Okay, so that's the answer to the question. All right, this is a very nice trick. You can do a lot of squares like that. For instance, 203 squares. If you're close to 100, then it's even better. Like for instance, if I say, what is 203 squared? Yeah, I would say it's 203. It's closest to 200. So subtract, and it's three units away from 200. And you subtract 3 squared, add 3 squared. This is 203 minus 3, multiplied by 203 plus 3. A squared minus B squared. That's what we are using. It's A minus B into A plus B. You can use that for numbers. So it's 203 minus 3, which is 200. This is 9. And this is easy. 200 times this is 412. And that's 41209. See how easy it is to calculate a square. But you have to be close to a multiple of 10, multiple to 100, then it can be done. Okay, so we can now get on to the next problem. You used to create a string of 10 numbers using only 0 and 1. How many such numbers can you create? Now we've done this auto count, what we call the first counting principle and the second counting principle. I hope you remember that, because we use this quite often. You have to create a string which has got only zeros and ones in it. So what I'm going to do is I'm going to put 10 boxes, and then I can divide it up to 10. All right, so you got 10 boxes here. Now, in how many ways can you fill the first box? You can put zeros or ones. So there are only 2 ways. Here too, you can put 0 or 1. Here too. So in every one of them, you got 2 choices. So the total number of ways you can do this is 2 to the power of 10. And that is 1024. See, if you in each case you have to make 2 choices, and this is actually the second counting principle. It's almost the same as the first counting principle. In the first counting principle, you only have 2 boxes. First counting principle, you have only 2 boxes, and you have to multiply the 2 numbers out. You ask yourself, how many ways can the first box be filled, and how many ways can you fill the second box? But if you got more boxes, you call it the second counting. There's no reason really to call it 2 different names. Just call it the counting principle. Okay, now this is a very useful fact here, actually. Let me just tell you, see, this has got a lot to do with binary numbers. Binary numbers. You see, if you've got 0 and 1 in an electrical circuit, you can either have a off, the switch is either off or on. So this is how the computer works. You have these circuits where you have several of these choices where something comes on or off, right? And then some of them are on, some of them are off. So you have a vast number of possibilities. See, a vast number of possibilities. A TV screen, for instance, I think it's called 64-bit or something like that. You got 64. I think you got 4,000. 64 times 64, 4,096. I'm not sure exactly how it works, but each one is given a certain color. And that's how what you see you see a screen full of color. But each one of those 4,096 squares have got a certain color. And when you see it, you think it's just a dot, but actually it's that screen is divided up into 4,096. If I recall, something like that. There's another very nice application for this idea. And it's got a very, very beautiful application. I want to tell you this while we are talking about this. Now, an interesting question in mathematics is, suppose you have a set. I'll just give a simple example. A set has, say, 4 elements. How many subsets does it have? Now, what is the meaning of this? Now, suppose you're looking at a set now which has got, say, A, B, C, D. Right. You can have a subset. The subset is another set which has got the same elements as this. Right? So you could have, for instance, you can say, let's see how many subsets have got only one element. Right? Let's do it by counting the number of elements in the set. So you can have, this is a subset. These are the one element subsets. Or you can have a subset which has got 2 elements. So you got AB. You don't have to put BA now because BA is the same as AB. It's the same set. It's got the same elements. So you can AB, or you could have AC, or you can have AD, or you can have BC, BD, or you can have CD. I usually count like this. Take the first one and match it with all the others. Then I finish the first one, A. Then let me now get on to the second one, B. I don't have to bring in B, A anymore. I'm finished with it. So with B now, I can match it with B or C or B or D. I only got 2 more. So I finished all the B's now. And then I go to C, CD. And of course, you don't have anything left for D. So you got that. And then these are the 2 element subsets. Then you have also the 3 element subsets. Now the 3 element subsets are easy. All you have to do is to, if you got A, you can match it with B, C, D. In other words, you're removing one from there. What are you left with? Right? And here B, you remove one. What are you left with? A, C, D. You remove C. What are you left with? A, B, D. And you remove D. What are you left with? A, B, C. So the 3 element subsets is exactly the same as the number of 1 element subsets. Right? Because each time you have a 1 element subset, you have a 3 element subset. All you have to do is to say what's left over. And likewise, if you have a 3 element subset, right, you can find out what's left over to get a 1 element. So the number of 3 element subsets is the same as. So these are the 3 element subsets, and then the 4 element is only 1. Okay, so now if you start counting the subsets having 1, 2, 3, or 4, we saw that there were 4 of these. And here we got 6 of these. See? 1, 2, 3, 4, 5, 6. All right. And the number of 3-element subsets is the same as number of 1-element subsets. Right? We show them what they are, and there's only one here. So if you add them up, you'll get 15. But actually, there is also another subset which is always counted, and that is a subset which has got no elements. You know, you put nothing inside it. It's called the empty set. Okay? No element. So often, even that element, that set is counted. The set which has got, subset which has got no elements. Right? So if I put 0 there, that means this is a set with no elements, and there's only one. We say there's only one empty set. Okay, so altogether, how many subsets have you got? You can add, you have to add all these things. You get 16. So this is just listing all the subsets of a set having 4 elements. There are 16 subsets. See? So I've answered the question. I can say a set has 4 elements, it has 16 subsets. Now, interestingly, if the set has 3 elements, it's got 8 subsets. You can try it out. It's easier to do. This one has got fewer subsets. I can put 3. Here it's got 8 subsets. It's harder to look at a subset which has got 5 elements. It takes you some time to list all of them, but you'll get 32 subsets. And you can see there is a pattern here. So we really have a set having n elements. Has 2 to the power of n subsets. The 32 is 2 to the power of 5. This is 2 cubed. It's 2 to the power of 4. So for 4, it's 2 to the power of 4. 3 is 2 to the power of 3. 5 is 2 to the power of 5. And n will be 2 to the power of n. So this number here, we said it was 2 to the power of 10. Right? You've got strings of zeros and ones. The number of such strings you can have is 2 to the power of 10. It's the same as this. Now, there's actually a way of proving this. In other words, if I ask you, how many subsets does a set having n elements have, right? The answer is 2 to the power of n. But how do you prove that? Well, let me just take all these things out. Okay, now the way to do that, it's very clever. There's a way of proving. Let's take 5. I don't want to write down all those 32 subsets. I want to find some clever way of counting the subsets. Okay, so what happens if, suppose the set has 5 elements, n equals 5. The question is, how many subsets does such a set have? All right. Okay, let's just call them A, B, C, D, E, for instance. Now, this is the A box. This is the B box. C, D, E. Right. Now, suppose I take a subset like C, E. Now, this is a C, right? So that I can put a tick here to say this is C and this is E. Right? So it's as if, so this is my subset that corresponds to CE. Okay. So if I take any subset, like for instance, if I take a subset like the whole thing. Suppose I'll look at this subset, A, B, C, D, E. Then A is in, B is in, C is in, D is in. So what happens is each subset corresponds to a ticking of these boxes, right? If I didn't have E, for instance, if I had just A, B, C, D, then I would have had that thing. And the E box would be, I'll have to put a cross there. This box here, I'll have to put a cross to show that it's not in. Right? So if it's not in, I put a cross. If it's in, I put a tick. So the question is, how many ways can you fill this thing up with ticks and crosses? You see? Now you can see the whole thing is, because by putting ticks and crosses, you're creating a subset. You're counting, you're identifying a particular subset. Each time you have a subset, you have a collection of ticks and crosses. See? As I showed you now. Right. So instead of counting how many subsets there are, you ask yourself, how many ways can you put ticks and crosses in the slot here? He says it'll be the same as counting the number of subsets, because each subset corresponds to a string of ticks and crosses, and each string of ticks and crosses corresponds to a certain subset. Like this one here corresponds to a subset A, B, C, D. That is not in. Right? So the question is, how many ways can you do this? And now that immediately tells you the story now, because you can either put a tick or a cross in any one of these. So this can be filled in two ways, either a tick or a cross, tick or a cross, tick or a cross, tick or a cross, tick or a cross. So the total number of subsets is 2 to the power of 5. Very clever. Right? So it doesn't matter whether there's 5, you could have 100. So the same argument will work, that you have to fill a string of 100 boxes with ticks or crosses, and each time you have a string of ticks and crosses, you have a subset, right, of that 100 element subset. So this number here, 2 to the power of n, is a very interesting number. It represents the number of subsets a set having n elements has. Okay, so always remember that. Okay, I hope you managed to follow all that argument. So now we're going into all right, so the next one, again, it's a counting problem. How many paths are there from A to B if you can only move downwards and to the right? So you're going to travel from A to B, and you can move downwards and to the right. So for instance, I can move to the right. It's a path, so I'm going to carry on. I can come down like this. I can go downwards, or I can go to the right. And I carry on going to the right here like this, and then come down. So this gives a path. Right. Now you can have many such paths. You can well imagine. Okay, you could have had you can go downwards or to the right. Okay. Or you could have had some other thing. You come do this, do that, do that, do that, do that. So there are several parts. The question is, how many such parts are there? Now, this is a very popular problem. And the observation is the following. Now, I want you to listen very carefully here because we just consider a single cell. Let's take a single cell. What I'm going to do is, from A now, I'm going to put a number here. This number will represent the number of parts to this node. We'll call all these are nodes where these lines cross. And at each node, I'm going to put a number. And the number will represent the number of parts from A to that particular node. Now, there's only one way in which you can reach this one, like this. I'm going to put a 1 there. Even here, there's only one way. I'm going to put a 1. Even here, only one way you can do this. Because you're only allowed to go to the right and bottom. Once you go to the bottom, you can't get back to that first row. The same thing applies here now. Right? Now let's look at this first one here. I've got a 1 here, and I've got a 1 here. And this is A. Now, in how many ways can you get to this? Now, you can get to this in only one. You can go like that, or from here to here. Okay, so to get to this, I can get to it from here, or I can get to it from here. Those are the only two ways I can get to this one, from the top or from the left. So if there are so many ways here, if there are m ways to get to this point here, and if there are n ways of getting to this, right, then to get to this here, you've got the m ways along this path, and along that path, there are another n ways. So altogether, it's m plus n. To illustrate now, for instance, here you got 1 and you got 1. 1 plus 1 is 2. Now, what I'm saying is that there are two ways of getting to this point here. And you can see what the two ways are. That, and that. Those are the two ways. Now I've got 1 and 2 here. So this one will become 3. See, you have to look at the other diagonal and add them. 3. Now, so what are the 3 parts? You can get to this only in one way. That and that. That's your 1. Now here, there's another path. I can get to this in 2 ways. I can get to that, and there, or that, and there. So now you can see that, and finally that. So that is those 3 parts. Right? So you have to add these. Now, the same way you go 3 plus 1 is 4. Here, 2 plus 1 is 3. 3 plus 3 is 6. 6 plus 4 is 10. So there are 10 parts. Once you've got a square and once those numbers are filled, then that number is automatically filled. Because you simply add those numbers to get to this one. That is the crux of what I've been saying here. So the square here can be, this rectangle here can be completed with that. Now you got that, and so on. So as you keep filling in these, you can get more and more. See, this is a very, very useful way of counting the number of parts you can get from A to B. There are many such problems in Olympiads. Right? Sometimes you might have a situation where, say, they tell you, look, you can go through all these, but you're not allowed to go through this. You're not allowed to go through that point. No-go area. Now, how many parts are there from A to B? So again, you'll do the same thing. You can go from here, 1, 2, 1, 1, 1, and you go 2 and 1 is 3. Right. But now here, you can't get to this. So the only number you can add is that one, 3. This is 0. You can't get to this point. So therefore, that can be assigned 0, because there's no path which leads to this. No, wait a minute. I'm sorry. You're not allowed to go in here. Right? So there's no number here. So that gives you, there's 3. And here, again, it's 1. You can only get to this. And so this becomes 4. So only 4 parts which go from there to there without going through this. That's 1, 2, 3, and 4. Avoiding that completely. Okay, so the same principle applies even if you got some other facts which are given. So they have variations of this in all these counting problems. Okay, now there are some chats here. Let me see. Right, so Surit is saying, I am in the car. When I get home, I'll switch from my phone. Surit, are you back with us?
Yes, Prof. I've got my
good.
iPad.
Are you at home now?
Yes, Prof.
Okay, good. All right. So let's get on to the next problem. Okay, the diagram shows height, A, B, C, D. All right. Now, kite is a very popular figure in geometry. In fact, there are various very important figures in geometry, apart from the triangle. The triangle is the three-sided plane figure. So you have a triangle. And amongst the triangle, the important triangles are the isosceles triangles, where 2 sides are equal, or an equilateral triangle, where the 3 sides are equal. Right? So amongst the triangles, you got the triangle, isosceles, and equilateral. The nice thing about isosceles triangles is that you can split them down the middle to get 2 equal triangles. These 2 triangles are identical in every respect. You can only do that in isosceles triangles. You can't do this in this. When you go down the middle, you don't get 2 identical triangles. So if these, in isosceles triangle, from the vertex where the 2 sides are equal, you split it down the middle, and they become equal. Like for instance now, if you were asked to calculate the area of an isosceles triangle whose sides are 4, 4, and 6, what's the area? Now you'll say it's half base times height. So you can draw the height sorry. This is very bad. I don't like to be untidy. Let's just draw a nice, decent triangle. We've got all the equipment here, too lazy to use it. So if you've got a thing like this, say 4, 4, and make this 3 because it looks smaller. What is the area? So the way to do that is split it down the middle. These are two equal triangles. So let's split it down the middle. And when you do that, as I said, you've got two equal triangles. So now these two are identical, which means that all the properties are the same. In particular, these two will be equal here. So you got 3/2 and 3/2. And then these two angles will also be equal because these two triangles are identical. So the two angles, they add up to 180 and they're equal. These two triangles are identical. The only way that can happen is when each of them is 90. So you got a right angle. When you spread it down the middle, you got two right angles. Right? And now that allows you to calculate the height because this is 3/2. So the height, the h, you can say h squared is 4 squared minus 3/2 all squared. This is hypotenuse. So it's 4 squared minus 3/2 all squared. That is, so you got 9/4. I think you got square root of 55/4 or something. Something like that. So once you got your height, then the half base is just 3/2 because the base is 3 times this. That's the area. So you can find the area of an isosceles triangle very quickly. And of course, the same thing can be applied to finding the area of an equilateral triangle. See? There's a nice formula for an area of an equilateral triangle. We can quickly derive it. Because the equilateral triangle has got all the sides are equal, so we can give a name to that side, right? So if I've got an equilateral triangle, let me just get rid of this thing here. In a case like this, I'd like to name, I don't like working with fractions like 3/2 and so on. And to avoid that, and we don't know what the sides are, so we'll give a name to the side. We can call it A and A, and then split it down the middle again, just like what we did before. But then we have, this is also A. All the sides are equal. So this is also A, and this is A/2. Okay, we can do that. So you got A/2, A/2. And then the height, h squared using Pythagoras minus the square of this, which is a²/4. So you can simplify this, you can come denominator 4, and you have 4a² minus a² gives you 3a². Right, so that's your h². So h is the square root of this. So you get the square root of 3, square root of a² is a, square root of 4 is 2. So the area, we've got the height now, the area of an equilateral triangle having side A, so A can be any number, is half base times height. The base is A, half base is A over 2. And this is the height we got here. Root 3 times A over 2. And there's the formula. Multiply all these. I'm going to put root 3 in front. A times A is A squared. 2 times 2 is 4. So this is the area of an equal triangle. Root 3 times A squared over 4. So if you know what A is, immediately you've got the area. You've got a formula for the area, right? If you know the side. So it's all coming out from isosceles triangles. Now, amongst the quadrilaterals, you got lots of interesting quadrilaterals as well. So you have a general quadrilateral. Any quadrilateral. There's not much to be said about a random quadrilateral, apart from the fact that the sum of the angles of a quadrilateral is 360 degrees, while the sum of angles of a triangle is 180 degrees. But in the case of a quadrilateral, the sum is 360. And that's very easy to see because all you have to do is to just draw this. And if you add up all these angles that you see in the picture, you'll get the sum of the 4 angles. This plus the whole thing plus this is the same as that plus that plus that, plus that plus that plus that. So you got 2 triangles. And the sum of each triangle is 180. So sum of 2 triangles 360. In fact, even if you don't have quadrilaterals, if you have some polygon, right? All you have to do is to start from any one corner, and from there you keep joining it to the vertices, and that way you split this thing up into several triangles. You see? And the sum of the angles of the original, how many have I got here? 1, 2, 3, 4, 5, 6. The 6-sided picture, the sum of all the angles is really okay. If you take this triangle and add them, or you take this triangle and add them, and this triangle, add the 3 angles, that triangle, add the 3 angles, you will see if you add all the ticks, you're going to get this 4 ticks here will make up this angle. The 1 tick here is here, and here these 2 ticks will make up that angle. These 2 will make up that angle. These 2 will make up that angle, and there's 1 here. And there are 4 of them here. So if you want to know what the sum of the 6 angles are, you simply have to add up all the ticks. But then this thing here, these 3 give you 180. Those 3 give you 180. Those 3 give you 180. Those 3 give you, there are 12 ticks altogether. And therefore, the sum of all the angles is 720. See, so you can add up all the angles of any polygon. Because you know the angles of a triangle add up to 180. But if you take a random polygon, if you do this, you'll see. So actually in a polygon, or having 6 sides, the sum of the angles is 4 times 180. The reason is that if you've got 6 sides, you can split it up into 4 triangles. See? If you've got 5 sides, you can split it up into 3 triangles. As we saw, when we had 4 sides, we can split it up into 2 triangles. Right? So in general, if you've got n sides, right, there is n minus 2 times 180. That is the sum of the angles of any polygon. Polygon is a general word for a figure with whose sides are all straight lines, having n sides. That's a nice formula to remember. If you want to add up a polygon having 47 sides, and you say, if you add up all the angles, what's the sum of the angles? You say, oh, that's easy. It's 45 times 180. Let's just reduce this by 2, multiply by 180, and you have that you've got, you add up all the angles. So you can see you get 8,100 degrees. Okay, now that's a general quadrilateral. You can't say much about a general quadrilateral, but there are special quadrilaterals. You can see I'm digressing. I'm not looking at these problems today so much because in each one, I'm giving you a quick lesson. All these things are very important, what I'm telling you. I'm giving you a lesson in geometry. Now, amongst the quadrilaterals, one of the simplest quadrilaterals is where you have one pair of opposite sides parallel. And that is called a trapezium. Only one pair is parallel, opposite sides. There must be opposite sides, obviously. Adjacent sides can't be parallel, meeting at the corners. Okay, there's not much to be said about this except that you can find you can have a formula for the area of such a quadrilateral, and the area is simply between the parallel lines. If you drop a perpendicular, then that is the distance between these parallel lines. They have a set. The distance is simply a vertical line that goes through the two parallel lines. So the area of this is half the sum of the parallel sides multiplied by the height between them. A very important formula. You must learn all these formulas. They are very useful. The area of a trapezium is half the sum of the parallel sides A and B, times the height between them. Now you might think, now where did that come from? It's quite easy. Actually, if you join the diagonal, then you have two triangles. So the area of this trapezium is the sum of the areas of these two triangles. Right? That is the idea. Now, can you work out the areas of the two triangles? Well, the area of the bottom triangle is half base times height. Now, that's easy to see. The base is B. Right. So the area of the bottom triangle is half base times height. But this one here is a little bit tricky. What is the area of that triangle? Now you have to look at the base to be that one. Right? That one. So the area of that is half the base, but the height now will be the vertical line from this point to that line. This becomes the height. The height of a triangle is from the vertex you draw perpendicular to the other side. It doesn't intersect the other side because this is an obtuse angle, but this is the height. So the area of this triangle is half A times the height. But you can see this height is the same as that height. These two lines are parallel, so the height between any 2 points is always the same. So the area of this other triangle is half A times this, which is exactly the same as that. So the area of the trapezium is half BH times half AH. Half is a common factor. Even H is a common factor. Half H comes out here, it's B. Half H comes out here, it's A. And this is exactly, if you rewrite it, it's half A plus B times height. Half the sum of the parallel sides times height. Okay, so that you can say about a trapezium. And there are other things like a parallelogram and so on. So I'm not going to go into all those, but I'm just telling you the various types of geometrical figures that you have. You got a parallelogram where the opposite sides are parallel, and there's some beautiful results here. What are the properties of a quadrilateral where the opposite sides are parallel? It's called a parallelogram. As the name suggests, parallel, and ogram means opposite sides are parallel. The only thing you know about a parallelogram, the definition, is that the opposite sides are parallel. Now, from that fact alone, you can use geometry to make various conclusions. Very beautiful geometry, just using congruence. You can prove. It's not in the definition. The definition says this is what a parallelogram is. But you can prove that this equals this, that the opposite sides are actually equal. Right? You can actually prove it. See? And all you have to do is to just join a diagonal. And what happens, the idea is, when you join a diagonal of a parallelogram, these two triangles become congruent. And once they are congruent, then you can conclude that they are identical. So that will allow you to say that that equals that equals that. So the opposite sides become equal. And you can prove it using the definition only of a parallelogram by constructing a diagonal and concluding that these two triangles are congruent. It's easy to show they are congruent because you've got alternate angles and so on and so forth. And in this particular case, you have two angles on a side. There's a condition of congruency, and there you have it. So like that, now there are lots of properties of parallelograms. It'll be nice for you to go and check to see what are the various properties of parallelogram and prove it. Most important thing, prove them. See? So like for instance, the diagonals bisect each other. Interesting. When you join both the diagonals, it turns out that each diagonal cuts the other into equal parts. And this diagonal bisects this one, and this diagonal bisects the other one. And that's another property of a parallelogram. See? Like that, you've got various properties. And of course, you also have the converse. Sometimes you're asked to prove that some four-sided figure is a parallelogram. You have to prove it. And then you'll say, how do I go around proving? You're not given now. This time you're not given that this is a parallelogram. You're given some other stuff, and you're asked to prove that it's a parallelogram. So in that case, you've got some other theorems which tell you how to prove that something is a parallelogram. For instance, you can prove that the opposite sides are parallel. By definition, it will then be a parallelogram. But how do you prove that two lines are parallel? The way to prove that two lines are parallel is you simply take any transversal text and try to show that these angles are equal. Try to show that these angles are equal, right? From the given information. Once you prove these angles are equal, then you say, hey, but these angles are alternate angles. Therefore, they are parallel. See? Very subtle difference. If they are parallel, you know these angles are equal. But if you know the angles are equal, you can conclude that they are parallel. It's not given it's parallel, but you can conclude it's parallel if you know that a pair of alternate angles are equal, or a pair of corresponding angles are equal, or the co-interior angles add up to 180. You can prove any one of those, and then you can conclude that these lines are parallel. So you can prove that these lines are parallel by using that criterion. All right, and so on. Now, amongst all these pictures, you got a kite. Right? Now, this kite Let me just finish off this discussion here. So amongst the parallelograms, you have a parallelogram where one of the angles is 90 degrees. A parallelogram with one of the angles equal to 90 degrees. So then what happens is, you got a thing like this. One of the angles 90. Now because they are parallel, these two are co-interior angles, so they add up to 180 degrees. And I said it's a parallelogram. And these two are parallel, this is 90. So therefore these two angles are supplementary. They are co-interior. So therefore, even if one angle is 90, all angles are 90 in a parallelogram. So it becomes a rectangle. And now this is a special parallelogram. Then you have a special rectangle. A special rectangle is where all the sides are equal. A rectangle with all the sides equal. Right. And that's called a square. So a rectangle with all the sides equal is called a square. It's got lots of very interesting properties. A square, so the meaning of it is it's a rectangle with all sides equal. But if you, amongst the interesting properties that it's got is when you join the diagonals, there are lots of nice things. But only in a square, you must be careful. Don't use these in every other picture. Square has got lots of interesting properties that the general parallelogram does not have. So you must be careful that you don't start assuming everything. Like for instance, we know that all the sides are equal. It turns out the two diagonals are equal as well. Therefore, we said that it's a parallelogram. But since the diagonals are equal, you have these. But the other interesting thing about a square is that these two diagonals, they cut at right angles. So then you have 4 isosceles triangles, but they're right angles. So you have, because these are isosceles, so all these angles are 45 in a square. See? So these are various properties of a square. The diagonals are equal, they cut each other at 90 degrees, and they bisect the opposite angle, so you get all 45. Okay, that's because one of the angles, 90 degrees, you get a lot of interesting things that come out from there. But with a, in general, you could have a parallelogram. I mean, it's tilted here, but with all the sides equal. And that's another very interesting figure. A parallelogram with all the sides equal. That is called a rhombus. So a rhombus is a parallelogram with all the sides equal. It's a special parallelogram. The opposite sides are parallel, and all the sides are equal. We already know the opposite sides are equal, but now we have what adjacent sides are equal. So which means that you've got lots of isosceles triangles. See? If I join this, I got these two isosceles triangles. If I join this, then these two are isosceles triangles. And now you can actually prove, it's a good, interesting exercise, that these angles are 90 degrees. So in a rhombus, the diagonals will bisect each other because it's a parallelogram, but they bisect each other at 90 degrees. That's a special property of a rhombus. More than that, these two angles, opposite angles, are bisected. So you must go and check to see what the properties of rhombus are. And remember what the properties are. These are all interesting figures in geometry. So the last figure is this one here, a kite. Okay. So at last we come to the problem itself. The diagram shows kite ABCD. What is the size of angle ABC in degrees? Now that allows me to do a little bit of geometry here now. Okay, now I want to work out the angle ABC. How do I do that? Well, to do that, I'm going to join this diagonal. And when I join this diagonal, the kite now is divided up into two equal parts. Two parts. And they're actually equal. When I say equal, it means they are congruent. They're identical in every respect. So if you look at these two triangles, right, you got that's right, you can say in triangles ABC, ABC, and ADC. Okay, you have the side AB of the top triangle equals AD of the bottom triangle. This equals this. Then you have BC is equal to DC. That's the definition of a kite. A kite is where both pairs of adjacent sides are equal. These are adjacent. That pair and this pair. And then you have that AC is common. So it means that these two triangles are congruent because you got the three sides. The triangle ABC is congruent. All right. Now, the grade 8s might not understand this, but I'm just teaching you some extra geometry which you will learn in grade 9. If the three sides of one triangle are equal to three sides of another triangle, that's what we got. The three sides of the top triangle are equals three sides of the other triangle. Then the geometry theorem says that they are identical in every respect. It means that not only the three sides are equal, but all the angles are automatically equal, right? Now, like for instance, this angle here. Now this angle, it is paired off with a single stroke in the top triangle. So this angle, which is paired off with a single stroke, must be equal to the angle which is paired off with a single stroke in the bottom one. So these two angles are equal. Likewise, these two, this angle here is paired off with a double stroke, and this angle here is paired off with a double stroke. So we don't put the dots now, we put different sign because these angles need not be the same. You can see this is slightly larger than that. Okay. But then now you got the 40 degrees now is divided up into two equal parts. So therefore this part will have to be 20 degrees. And the 70 degrees now is divided into two equal parts. So this is 35 degrees. And lo and behold, you've got two angles of this triangle. And the question was, what is this angle? ABC. So in this triangle, you've already got two angles. So you can easily calculate the third one because all three of them add up to 180 degrees. And if you do the calculation, you'll see that angle ABC, 35 plus 20 is 55, subtracted from 180 and 125 degrees. Okay, so the idea is to actually draw this middle line, which you might not have seen. It's not there. It's not there in the picture, but it's called a construction. So you got a construction which solves your problem. Yeah? But you have to recognize that you have to do this to break this thing up into two equal triangles. Because that equals that, that equals that. So you got a good situation where you can create two congruent triangles, and then from there you can conclude that all the properties are the same. So this is a good exercise in congruence, and I've done it in full. That is how you do all the other things that I was talking about, parallelograms and so on, which I didn't prove. It's all about congruence. You just have to see what is given and try to prove some triangles congruent and make. Then you say there are three things in one triangle are equal to three things in another. Therefore, all six things are the same. That's what you mean by the theorems of congruence. Very, very powerful result. And if only three things you know of one triangle are equal to three things of another, then you can conclude that those triangles are identically the same. Okay, so that takes me now to the next problem. So you got lines A, B, and D, E are parallel. This line here is parallel to this. And angle CDE is 40 degrees. CDE is 40 degrees. So, it's always nice to write down the information that you are given into your diagram. Your diagram, you can see things very clearly. Now, what is this angle? And now this is 90 degrees here. So how do you use these in a parallel? Okay. Now, here also you have to have a construction. And once once you get used to this kind of a thing, you'll be able to see the construction very quickly. I got two parallel, but it'll be nice to draw from C. I'll draw another line which is parallel to these two. I'll draw a new line parallel to any one of them. Of course, in that case, obviously all three lines will be parallel. These two are parallel. So you draw a third line which goes in the same direction as the other two. Now, once you do that, then you can see the things open out nicely now, because you got 40 degrees, and now you got a Z angle here. So these are alternate angles. So they're equal. We know they are parallel. This is by construction. It wasn't there. So you include it in this picture, and then you can say this is 40 degrees. But now you know the whole thing is 90 degrees. And this part is 40, so this has to be 50. Right? So that part has to be 50 degrees. But now you got these two lines are parallel, and X and 50 are U angles. There. These are U angles. So they are supplementary. In other words, they add up to 180 degrees. So X plus 50 is 180. Co-interior angles. You call that co-interior angles. Co-interior angles always add up to 180. They are the U in a pair of parallel lines. See? Those are co-interior angles. Okay. Now, therefore, you can solve for X. What must be added to 50 to get 180? The answer is 130. So this problem is an interesting problem because without this red line, it would not have been easy to solve. I'm not even sure whether you can solve it. I don't know whether it's possible to solve it. But maybe there's another way of doing this thing as well. It just occurs to me. So we got X is 130 degrees. Just remember that. It occurs to me that there is another way of doing this thing, but you have to have a construction like before. Suppose I did this. This is part of a transversal, BC. So why don't I complete it? So now I have a full transversal between these parallel lines. That's useful because once I got a transversal, I can do things with it. Okay, so now what can you do with this? So you have, well, you're just extending this line, right, to create the full transversal. So therefore, the remaining angle, this is one angle is already 90 degrees. So this is also 90 degrees, the straight line. Right? Now, you got a U angle, but it's up here now. That. And this is X. Oh, we had this is 40, yeah? Yeah, this was 40. Okay, so this is 40. Now, in this triangle here, this new triangle which I've created, I've got 90 and 40. So they all of them add up to 180. So this has to be 50. But now you can see you got a U angle here, and the X plus 50 are co-interior angles, X and 50. So that gives you X equals 130 degrees also. So there are two constructions that you can make here, and both of them will lead to the same answer. But in both cases, you need a construction. Without a construction, you will not have been able to do this. Okay, so the next problem is an assignment problem. So it's an interesting assignment where there are lots of applications. The main thing is a rectangular sheet of paper with sides. So there was a sheet of paper originally in this picture. A sheet of paper was something like this. So this was a sheet of paper, and then it has been folded. So this part is folded over this. You can see this fold here. So originally it was a rectangle like that, and now it's folded. The point about this is that this triangle here is sitting on top of this triangle. So these two triangles are identical because they are one is sitting exactly on top of the other one. Yeah? So all the sides and all the angles are equal. So now, so that's very important. Once you got this picture, then you are supposed to ask to calculate D. So just remember that this is what you had originally, and it's now folded, and you can try to calculate D in some way or the other. That's an interesting problem. It's not too difficult, but I'm sure some or many of you can work it out because you guys are the few people who have actually took the trouble to come and attend this class. So I'm sure you like geometry and you'll be able to do this. It's a very nice, interesting problem. All right, you have to use Pythagoras and you have to use isosceles triangles and so on and so forth to solve this. Okay, so let's just get on to the next problem. The 6 angles of 2 different triangles are listed from the largest to the smallest. Okay, so you got 2 triangles, and therefore there are 6 angles. All right, that makes sense. So let's just draw these triangles. Now, I'm not drawing them to scale. I don't know what these angles are. So you got 2 triangles, 2 different triangles. Okay, that's the starting point. And the 6 angles are listed from the largest to the smallest. So the largest, like for instance, the largest, this looks like 120 here. This is the largest. You can see it's obtuse. And this looks quite big here. Let me make that to be the next one. 80. And this one is 65. And the smallest is 37. But all this is just guessing. We don't know. Maybe the 80 is on this side. Maybe 65 is on that side. So we just have to be careful because I've just drawn them like that. So that doesn't mean these are the angles. Okay, so you got 120, 80, 65, and 37. So I'll draw my 2 triangles. And now I ask, 120 is, let's start with 120. Now, we got 80. Can 80 be an angle in this triangle? Right? I'm sure you all know. Right? You can put your answer in your chat group. Can 80 be an angle in this triangle? You have to tell me why. Nobody? I'm looking at my chat here to see if you can answer yes or no. Right, so one person. Anybody else? There's only one person from 9 who knows that 80. The question is, can 80 be in this triangle? I don't know. Surit seems to have said something. Oh, you messaged this thing. David, I can't read the message.
Okay, Prof. Let me check.
All right,
No,
so
it's just saying is Tristan says no, as the interior angle of a triangle add up to 180.
yeah,
If
right.
you add
Okay, that's correct.
80, it will be
It says you
actually,
can't have 80 here. Because
yeah,
otherwise you already got 200 degrees. They all add up to 180, so it's impossible. 80 can't be here. So 80 is in this triangle. The same way even 65. So these two add up to more than 180. So 65 has to be here. Right? Now you got two angles of this triangle. So it's 80 plus 65 is 145. So this is 35. Right? You also got 37. Now this is filled up now. So 37 is in this triangle. Then once you got that, then 120 plus 37 is 157. You got 23. Because they add up to 180. So now you've got all the six angles. So it's 120, 80, 65, 37. And the next one is 35. Putting it in descending order, 35. The last one is 23. In degrees, what is the last angle on the list? The answer is 23 degrees. That's the smallest angle. Okay, so the big thing was you can't put 80 in the same triangle where 150 is. And the same thing with 65. So that helps you to march forward in this problem. I'm surprised that only, a lot of people have answered this one. Okay, it came up a little bit later. David, I don't know why I can't read what they are saying. Oh, okay. No, because the sum of the interior angles is also 180. If you add 180, it'll be higher than 80. Okay. So we got one person ZU. And like that, I don't know what the others are. Okay, that's good. ZU has answered that correctly. And I can't read the other ones. check to see whether you have answered them correctly or not. David, you must help me with this so that I can read all the messages when they do. Write down the messages. Okay, so the next problem is this one. In the sketch, adjacent lines are at right angles. So you got, this is 90 degrees, this is 90 degrees. Find the integer n, that's a whole number, such that n is less than AC plus AD less than n plus 1. Okay, so it means now AC, I need to work out what AC is. Now, AC is easy to calculate because AC is the side of a right angle triangle whose sides are 3 and 4. So you use Pythagoras, and 3 squared plus 4 squared, you'll get this is 5. Right. And then you got AD also. Now, how do you find out? How do you find AD? That's an interesting thing. You've got this is 5, you got this is 13. But these are parallel. You see, these are two 90 degrees here, right? And because they are both, they are right angles, so because those are 90 degrees, it means they are co-interior angles. And these co-interior angles add up to 180. See, that's what you know, that when you add these angles, you get 180. But if the co-interior angles are supplementary, as I told you, then you can conclude these lines are parallel. And the various ways of showing the two lines are parallel, you can show a pair of alternate angles equal, or a pair of corresponding angles equal. All co-interior angles are supplementary. In this case, we got that. So these are parallel. But now you've got a part of a rectangle here, because these are parallel. So why not complete the rectangle? I want to calculate AD, you see. So AD is, if I complete the rectangle, then I can use Pythagoras, you see. So all I do is to just drop a perpendicular onto the next line. And now you have a parallelogram with one of the angles equal, and I told you that's a rectangle. You can, right, now this is a parallelogram because now the opposite sides are parallel, because this is 90 and 90. So in a parallelogram, the opposite sides are equal. If this is 3, this is 3. Well, you already know that this opposite sides of a rectangle must be the same. So this part is 3. So therefore, the whole thing is 13. So this part is 10. And so can we calculate AD? Well, we are nearly there. We've got a right angle triangle. We've got one side is 10, but we don't know the other side. Oh, but this other side is the same as this, because this is opposite sides of a rectangle. So the construction is to draw this thing here. That wasn't there. AC you have to draw because you mentioned AC, but this wasn't there. So your construction is to drop a perpendicular from A to DC. And once you got that, then you got a right angle triangle whose sides are 10 and 4. So you got AD squared, right, using Pythagoras, 10 squared plus 4 squared. This is 10, that is 4, that gives you 116. So AD is square root of 116. So now you got AD and you got AC, which is 5. So I want to find N such that AC is 5 plus square root of 116 is less than N plus 1. And N is an integer. So how do you calculate this integer? So these n and n plus 1 are consecutive integers. They are next to each other. So it's nice to know this. The only bad guy here is square root of 116. Right? Can you decide what two numbers it is between two consecutive numbers? Well, that's what we need to find out. Then we'll be able to solve the problem. Because this thing here is 10 point something. 100 is 10. Now, this is greater than 100, but it's less than 121, which is the square root of 121 is 11. So this lies between the square root of 100 and the square root of 121. In other words, it lies between these two. These are those integers, you see. So that's what you've got. So now all I have to do is to add 5 to both things. And I get 5, because this is the quantity I'm looking for. When I add 5 to 10, I get this. When I add 5 to this. If I increase all these numbers by 5, inequality still remains the same. So you get 5 plus 10, 5 plus this. Now you can see that this quantity lies between 15 and 16. Right? And these are the two consecutive numbers. So n is 15. So the idea is to find out between which two consecutive numbers. Okay, n and n plus 1 are consecutive numbers. They're next to each other, integers. Right? You're adding 1 to an integer, it's the next integer. So you have to find out between which two integers is this. The answer is 15. Okay, and then that allows me to just, okay, once again, I'm taking too much of time, but today I taught you a lot of things, a lot of geometry. So now this is an interesting problem here. I'm going to just rush through this. Find the perimeter of the indicated triangle. Now, what do you mean by perimeter? Perimeter means the sum of all the boundaries, the full length of the boundary. Yeah, the boundary consists of 3 sides. So you need to give names to these. So the problem is, what is A plus B plus 10? What is A plus B plus 10? It's a very interesting problem. You are given, this is the area. I should have said that 11 is the area of this triangle. I just pushed an 11 in between like this. That you have to assume that you are talking about the area. Okay, so you know its area and you know the hypotenuse, but you don't know the sides. And you need to calculate this. All right, so let's see now, what can we draw any equation? Well, certainly the one equation you can do is Pythagoras. A squared plus B squared is equal to 100. So you got one equation involving A and B. And because you know the area, you got a formula for the area. Because now you got this becomes the height. You see, if you take this as the base, the half base, that becomes the height from the vertex to that side. So the area of this triangle is half AB. So you got these two pieces of information. Now you can try to calculate A and B. The problem is that when you try to calculate A and B, you very hard. You get stuck with all kinds of complicated things. Right? And it becomes a very, very difficult problem. The thing about that is that you're not asked to calculate A and B. You're asked to calculate A plus B. Then I'll know the answer. So I need to calculate A plus B. Now, is A plus B connected with these? Well, there's A squared plus B squared. So, yes, it is connected, but I have to square it. Then you have a squared. Now, this, hopefully you know what a plus b all squared is. A squared plus 2ab plus b squared. Right? Now, even if you're in grade 8, you should always know that when you're squaring, the sum of two numbers is a squared plus 2ab plus b squared. I think I mentioned this at some other stage. I can put the a squared and b squared together because that is what we have. So if I just push this thing here, I got a squared plus b squared is 100. And you got ab. Let's see, what is ab? Well, if you multiply by 2, then the 2 times half is 1. So multiply on both sides by 2, you get ab equals 22. So 2ab is 2 times 22. It's 2ab. 2 times 22 is 44. 100 plus 44 is 144. And there's a plus b all squared. That's very nice. Because it's got a square root. A plus b is all squared is 144. So therefore, a plus b itself will have to be 12. Then I got that. So therefore, the perimeter is 12 plus 10, which is 22. So it's an interesting problem where you have to use your common sense. Say, what information have I got and what am I trying to get? We're not asked to calculate a and b. We're asked to calculate a plus b. So is a plus b related to, can I somehow manage to use these to calculate a plus b? I say, yes, I can, but I must square it. Then I know I'm going to get an a squared and a b squared. Then after that, the rest is history, as you saw. Okay, so that is how you calculate this one. I think some of you might want to take a photograph of this, but it will be in the post mail somewhere. Okay, and then we get to the last one. I think it's the last problem. Determine the area of this quadrilateral. Okay, we've already said something about the areas, so I can go a little bit quickly here. To find the area of a quadrilateral, we might as well just split it into two triangles. I've got a right angle triangle here, so obviously I have to join this, because then I can use this one. So what do you have? You have you've got two triangles. The area of this triangle is very easy. The base now you have to think of it as 4, and this is the height. So it's half 4 times 3. 4 times 3 is 12, and half of that is 6. So the area is 6 here. So we found the area of one triangle, but now you have to find the area of the other triangle. You got 5 and 6 here, but you got a right angle triangle, so obviously I have to go to Pythagoras to get this. And now here you see, I got 5, and I got 5, and I got 6. So this is a very special triangle. I spoke about this earlier. It's an isosceles triangle. And I even told you how to find the area of an isosceles triangle. I told you to find the area of an isosceles triangle, you have to split it down the middle. So we split it down the middle. And then, as we saw, then you could, these two triangles are identical. You have this kind of a thing. And these two are equal, because these two triangles become congruent when you split it down the middle. So now these become 3 and 3. Because these two are equal now, you see. In the isosceles triangle, when you split it down the middle, so the 6 is divided up into 2 equal parts. But now you got a right angle triangle with 5 and 3 here. So again, you use Pythagoras, and clearly it's this famous 3, 4, 5 triangle. All right. So it means now I can calculate the areas of all these right angle triangles. Here, the area of this right angle triangle, half base times height, 3 times 4, 6. This is also 3 times 4, 6. So the sum of the 3 areas will be the area of ABCD. 6 plus 6 plus 6. Okay, guys. So that takes care of all the problems we tackled today. And in many of them, we had extra lines, constructions, right? In Olympiad problems, very often you have to have construction. You can see even here, I have to get all kinds of constructions to solve the problem. In Olympiad problems, often you need to have constructions in order to solve them. But in school mathematics, I don't think you're ever asked to use constructions. So you have rather somewhat boring problems. But yeah, with Olympiad mathematics, you don't have certain piece of information and you can actually do it by breaking a complicated thing like this into 3 right-angle triangles. See how nice it is. Because I know everything about right-angle triangles. So why not, do it, break it up into something simpler. And for that, you need construction. Okay, so guys, I hope you enjoyed today's class. We said a lot of things. Right, I'm going to put don't go away. I'm going to stop sharing now. Right, if you think you enjoyed today's class, join up. Derek, Sunit put his hand up. Nobody